Hi, I'm going to do an example about magnetic forces and torques. This is problem 5-21 in the book. And we are given a situation where we have a loop of currents that are going around like this. And our axes are the x-axis, which is positive to the right, and then the y-axis bisects the triangle like this, like that. We have a magnetic field which is y-directed. And we're given the end points of the triangle corners, the triangle segments. So this is minus 10, 0. This is 10, 0. And this is 0, 20. And all of these dimensions are in centimeters. And the magnetic field is A hat Y 6 milliteslas. All right, and we are to find the forces and the torque on this loop of current. So, step 1, find the forces. I'm going to label these sides 1, 2, and 3 because that'll make it easier. We'll calculate the force on each of them and then add them together. So, finding force number 1. If we are calculating the force using the force integral, we have here I'll insert some math so I have room to write this. We have dF is equal to I dl cross B, where dl is our differential length, I is the current, and B is the magnetic field again. So then our total force is then the integral of dF around your circuit, which is equal to integral around the circuit of I dl cross B. In our situation, the triangle sides are each lines or line segments. So that really simplifies our integration situation, and we can just write instead that the force for one side, for a side, any old side, is equal to the current times the length vector for that side cross B. So that's its length and direction. All right, so for force number 1 on side 1, we have that L1 is going to be x-directed, and it has a length of 20 centimeters. You can see that by scrolling back up to that image here. We are looking at side number 1 right there. Its length is from minus 10 to plus 10 centimeters, and it is x-directed, positive x, because here we've got the current directed to the right. Current is going counterclockwise around our triangle in this situation. So in that case, we've got force 1 is equal to current times L1 cross B, which in this case is equal to 10 amps times 20 centimeters times I'm going to put the cross product at the very end. 6 milliteslas times a hat x cross a hat y. And a hat x cross a hat y just gives us the z-directed unit vector, a hat z. So then multiplying out all of these units, we get F1 is equal to a hat z 12 millinewtons. Now we're going to have F2 for the second side. Now the second side is at a bit of an angle. It goes from plus 10 on the x-axis, 0 on the y-axis, to plus 20 on the y-axis, and 0 on the x-axis. So it slopes back into the left a little bit. Let me redraw that. We're now looking at side number 2, which is this side. And it goes from 10, 0 to 0, 20. We're going in that direction. So, in that case, what do I have to do? I have to first find L2, the length vector for number 2, which is pretty easy. We can just subtract the endpoints from each other to get that, which is equal to minus 10 centimeters a hat x plus 20 centimeters a hat y. The force on side 2 is equal to the current times L2 cross B. B being y-directed, we don't get any contribution. Oh, I didn't want that to disappear though. We don't get any contribution from the y-directed part of L2 because when you cross a hat y with itself, you get 0. We're only going to get a contribution from the x-directed part. X cross y again is ax cross ay is again az, but now we have a minus sign on this minus 10 centimeters here. So we're going to get a minus z-directed force here. And we've got only 10 centimeters rather than the 20 that we had on side 1. So force number 2 is going to be minus a hat z 6 millinewtons, half as much as F1 was. Next, we are going to do force number 3. Now the length vector for side 3 is going to be, again, by subtracting the endpoints of the wires, we get minus 10 centimeters a hat x plus minus 20 centimeters a hat y. But again, we don't really care about the contribution of the a hat y because a hat y cross itself is 0. So, force number 3 is again going to be 10 amps times minus 10 centimeters times 6 milliteslas times a hat x cross a, whoops, wrong a hat y. And that just gives us a z direction, and we get the minus sign from right there, from the minus 10 centimeters. There. So, looking at this, we find that F3 has the same magnitude and direction as F2. It's minus a hat z 6 millinewtons. And that's that. Those are the 3 forces on our triangle. So if we were to draw that again, we've got our triangle here. The bottom, the base side, side 1, experiences a force of 12 millinewtons coming out of the page, and the other two sides, sides 2 and 3, experience a force of minus of 6 millinewtons, 6 millinewtons each going into the page. So the next thing that we are asked to compute is the torque. There's two ways to do torque, the long way and the short way. Luckily, we can do it the short way here because we know that the torque on a current loop in a uniform field is given by the torque is equal to the magnetic dipole moment of the loop crossed with the magnetic field. That's pretty easy. And that magnetic dipole moment is equal to the current times the area times the surface normal vector. And that normal vector is defined so that if you use the right-hand rule, it points in if you use the right-hand rule and align your fingers with the direction of the current, your thumb will point in the direction that the surface normal vector will point. So right-hand rule for that one. So that makes our life easy. We know the area of the triangle. So then the torque is going to be 10 amps times 1/2 base, which is 20 centimeters, times height, which is also 20 centimeters. The surface normal vector for that is in the z direction. And then we're going to cross that with the magnetic flux density, which is 6 milliteslas in the y direction. AZ cross AY gives us a minus x. So our total torque works out to be minus a hat x 1.2 millinewton meters. Or if you wanted to write that not using millinewtons, it would be 0.0012 Newton meters. Have I got the right number of zeros there? Yes, I do. Now that was the short way to calculate it. The long way to do it would be 1, find the center of mass. Because we have to, because the triangle, since it's free to rotate, will rotate around its center of mass. And then 2, the differential unit of torque is going to be the lever arm crossed with the differential unit of force, where this lever arm r is the vector distance from the axis of rotation to dl, your differential length at which you're calculating df. But you only have to do it the long way. Oh, and then you would, step 3 would be integrate to get the torque. But you only have to do it the long way if you have a non-uniform magnetic field. And since we are not mechanical engineers, usually when we are designing